Part 2.
Let's first look at how MEMS are made. The manufacturing process is similar to that of typical microelectronic products and uses the same materials, silicone for example. Extremely thin layers of various materials are deposited onto a base. This is the deposition stage. After this, a pattern or design is transferred onto the layers. This is usually done using a photosensitive material, a material which changes its physical properties when exposed to a radiation source, such as an electron beam or X-rays. The important point here is that the material is not uniformly exposed to the radiation. Some of it is masked, and so we've got two parts. The properties of the two parts become different. The parts of the material which were exposed develop different properties from the parts which were hidden. These differences can be exploited, and exposed parts removed by dissolving them in a chemical solution, such as an acid, or by allowing them to react to a gas or a combination of gases. This process of removing parts of a layer is known as etching. Etching leaves a microscopic three-dimensional surface. In this way, both electrical and mechanical components are constructed. Now let's look at some applications of MEMS. First, I want to talk about car crash sensors. The MEMS that are used here are a form of accelerometer. They measure changes in the car's speed. Inside the tiny device, there is a weight attached to a spring or a hinge, and this mass moves as the car slows down or speeds up. The MEMS contain electrical sensors that can send data about the movement of the mass to a microprocessor, which monitors this information. In a crash, there is a sudden negative acceleration, a deceleration, and when this reaches a certain critical level, the airbags open. All this happens in a fraction of a second. Now, airbags in cars have been around for some time, so you might wonder, what's so special about using a MEMS for this? Well, I have a colleague who's been directly involved in the development of these new sensors, and she has no doubt that the use of MEMS has meant a huge improvement on earlier versions, making the sensors more reliable, and this means safer as well as cheaper. Another product that has been greatly improved by the use of MEMS is the video projector. Do you remember I talked about some MEMS being actuators? Well, this is a case in point. These actuators use micro-mirror devices to improve image quality. Micro-mirror devices consist of extremely small mirrors attached to hinges. The mirror can move on the hinge in two directions: towards the light source, which means the mirror will reflect the light, or away from the light source, which means the light will be blocked. Each mirror corresponds to 1 pixel of the projected image. So, if the mirror reflects the light source, there will be a tiny point of light on the screen. Not only that, but the amount of time the mirror reflects light will also give the perception of brightness. The longer it reflects, the brighter the point. In this way, up to 16 million different shades of color can be achieved. Now, this is a massive improvement on previous technology, to the extent that it is now being used in cinemas and replacing old film projectors. Some people say that MEMS don't bring anything new to electrical engineering. It's simply a case of making existing devices smaller. But the evidence shows that this is not really the whole story. In my view, both the examples I have presented today show how MEMS can improve existing products, making them more reliable and more accurate, and sometimes doing the task more cheaply. If we don't recognize the benefits that MEMS can bring and act on them, we could get left behind, and that would be a disaster. As Feynman said in his excellent talk, the whole of technology benefits as a result of developing smaller-scale devices. Actually, MEMS are destined to become more and more important in the future in all sorts of different ways. Now, I'm going to stop at this point and